Hey, it's Mr. Robeson. We are back in calculus and we are back at looking at limits. So in our last episode we looked at just the very basics of what a limit was as a function approached some x value from both sides, what happened to the function value. In this episode we're going to look at some cases where the limit does not exist. So first up we're going to take a look at the limit as x goes to 0 of the absolute value of x over x. Alright, well, if we tried to plug in 0, we're going to get 0 on the top and 0 on the bottom. So that's a problem. Especially 0 on the bottom for us is a problem because we can't have 0 on the bottom of a fraction. So what we're going to do is we're going to break this up into a piecewise function. Alright, so we take the absolute value of x and we say that that is equal to, well, if the number is positive, it doesn't do anything. So it's just going to be x if x is greater than 0. And if the number in here is negative, the absolute value is going to change its sign. So the way we say change its sign is we put a negative out in front. So we get negative x if x is less than 0. We can put the equal to on either one. I'm going to put it up here on the top one. So we're going to replace it by that. So now if we have just x over x, so let's put in back over x for each one of these. So this would be over x, and this would be over x. So that means this one is just 1, and this one is just negative 1. So it's just 1 when we're greater than or equal to 0, and negative 1 when we're less than 0, but now we can't have the equal to because we had 0 on the bottom, so we're going to get rid of the equal to here. So we got to get rid of the equal to here. So we scratch that out. And now let's take a look and see, is the graph there? There's the graph. All right. So we're negative 1 when we're down here. So when x is less than 0, we're down here. When x is greater than 0, we're up here at 1. And what ends up happening is, well, we're walking around down here, and then we take a big old jump up to here. So what we call this is a jump. Alright, so what happens with the limit? Well, from one side it's down here at negative 1. From the other side it's up here at positive 1. And since it goes to two different values from each side, we say the limit does not exist. Alright, so we say does not exist. Or sometimes we write that as DNE for does not exist. Alright, let's take a look at the next guy over here. So we want the limit as x goes to 0 of 1 over x squared. This is a period. This is not part of the problem. It's just the end of a sentence. Right? So if we take a look at this graph, I know if I plug in 0 on the bottom, that's a problem. In fact, it doesn't cancel out, so it's a non-removable discontinuity. So non-removable. I think there might be an E in there. Discontinuity. All right. It's also a vertical asymptote. So we can look at it here and we can say, okay, that is also a vertical asymptote. Vertical asymptote. Alright, so as we go to 0, this graph's just going to keep going up forever on this side when it's less than 0. And when it's greater than 0, this graph is just going to keep going up forever. So it's going towards positive infinity. Alright, so with limits, we don't really say they go to infinity, or if they do go to infinity, we generally just say that they do not exist. Alright, so we're going to say this does not exist for now. Alright, so if we have a vertical asymptote and we're taking the limit at that vertical asymptote, we say our limit does not exist. Alright, another strange case. So you may have seen this before, you may not have. So discuss the limit as x goes to 0 of sine of 1 over x. So this is inside the sine function here, sine of 1 over x. If we go to 0 in here, we get 1 over 0. That's infinity, positive or negative infinity. So sine of infinity, well, I know the sine curve just kind of keeps going back and forth like this. But as we go to infinity, is it at the top, or is it at the bottom, or is it at 0? Like, what's going to happen? Right, so I'm going to graph this. Remember we said we could look at a table, we could graph, or we could try and use algebra. So here's the graph. Well, that's not much help. There looks like there's a big jump in here. All right, so let's try and zoom in. Enhance. Well, we got a little closer, and there's still this big jump from here to here. We're not really sure what's happening. But it looks like it's zigzagging pretty fast here. Let's try another one. Enhance. So we're zigzagging even more, and again, we're not really sure what's happening here. This looks like it might be 0. Enhance. It's just going back and forth an awful lot. Right? In fact, if we kept zooming in, it would just be going back and forth so much that we couldn't even tell where it was. It's basically a solid line between -1 and 1. So this function does what we call oscillating, or oscillates. It should be an L, oscillates. All right, so since it's oscillating so fast in here, we can't tell what it's going to or what its function value is going to be, if it's going to be up at 1 or down at -1 or 0 or anywhere in between. So again, we say that this limit does not exist. All right, so those are our 3 cases where we have problems. So if we have approaching 2 different values from each side, or that's a jump. All right, if it increases or decreases without bounds, so it could go down too, that is our vertical asymptote. All right, or it can oscillate. Look, it's 2 L's. All right, so the function can go back and forth really, really quick, and we can't tell what's going on, so then the limit there would not exist. And it have to be 2 different values. If it oscillates down to the same value, then that's not a problem. All right, and the other thing, I just wanted to show you this. We're not going to do anything with it, but this is the actual definition of a limit. So as x approaches c from both sides, limit as x goes to c of f of x equals L, the function value of f becomes arbitrarily close to L. So if we go a tiny, so here's c right here in the middle. Here's c. If we go a tiny bit above c, and we're going to use the number, the symbol delta, that is a lowercase delta. And we're going to go a tiny bit below c, again another lowercase delta, and delta is just some number greater than 0. It's very small. Then we're right around here if we plug it in, and we're up here if we plug it in. And it's basically like when we use our table and we set our table step to smaller and smaller, these numbers get closer and closer to one particular value, and that one particular value that they get closer to is our L, our limit value. All right, so that's the actual definition. That's actually what's going on when we do our limit. All right, or in other words, it's within some sort of epsilon, which for epsilon could be as small as we want to make it, but it's within epsilon of the actual limit L. And we just keep making epsilon smaller and smaller, and we end up just getting L. All right, don't worry too much about that formal definition. That formal definition is not going to be on the AP exam, and we won't have anything about it in class. All right, so today, from this little video, we just want to know when limits don't exist. So we had jumps, we had vertical asymptotes, and we had oscillating. So those are our 3 cases when limits don't exist.